to be back for this second session of the ANTS Summer School. So for the first talk of the day, we're happy to receive Jan Boti, who comes from Singapore, and who is going to enlighten us with the mathematics of isogeny-based cryptography. So.
Well, kia ora. So I finished my PhD in New Zealand. It's a real pleasure to speak here. Thank you for the organizers for organizing this. I think it's very well done. So today I'll talk to you about mathematics of isogeny-based cryptography. And because this is more of a number theoretical seminar, I thought I'd focus more on the mathematical part of cryptography and show you all the nice mathematics that arise from cryptography. So without further ado, this will be the contents. So I'll cover Diffie-Hellman key exchange. I'll talk to you about two different isogeny-based approaches. One is called SIDH, and the other one is called C-side. And after covering that, I'll talk to you about attacks on these systems. So I'll present attacks on SIDH and also on C-side. And you'll notice that, you will see actually more that these will cover a lot of deep mathematics and quite a lot of beautiful mathematics as well. So I hope you slowly gain to appreciate the beauty of this mathematically. So I'll begin with Diffie-Hellman. So this is a protocol where two parties will establish a secret key which will be known to both at the end of the protocol, but not to anyone else monitoring the traffic between parties. So we have two parties, Alice and Bob, and they begin with an abelian group with an element in the group. It can be a generator, and let's just take it to be a generator for now. So they agree on this group, abelian group, and a generator. They take a random n and a random m. This will form their secret. And what they will do is that they will compute x and y, which is going to be public. So you'll notice that I tried to put everything in red, those are values that need to be kept secret. And if it's in black, it should be public. So Alice computes x using g and n. Bob computes y using g and m. X and y would then be made public when they exchange these values via the public channel. And so Alice will receive y. She can use her secret n to compute g to the mn. Bob can do something similar on his side and also compute g to the mn. And notice that they will both obtain g to the mn because of the commutativity of the operations, because we are in an abelian group. And this is important, that is an abelian. So what does the adversary see? The adversary sees only the things in black, and he would like to try to work out the shared secret, right? So he will try to recover this GMN given G, Gn, and Gm. And to do so, he'll need to solve this, the Diffie-Hellman problem, which is given the values you saw before, recover the shared secret. So the question now then is, how do we solve this? Can we find a way to solve this? And also, notice that if you have the discrete log, if you are able to solve the discrete log problem, you can automatically solve the Diffie-Hellman problem, because you can just recover, given the discrete log oracle, you can just recover n. And given y, you can recover the shared secret as well. So that's good. So that is the basic protocol. And this is what we've been using for a couple of years now. But quantum computers are coming soon, as you may have heard. And this can break the Diffie-Hellman problem on top of the discrete log problem. And it's projected that the quantum computers will need about 2,000 bits. Right now we have like 50 qubits. So it's far away, but maybe not quite as far away. So we would like to find alternatives to using just abelian groups. So this is what we have, right? We have your G. This is your generator. This is what Alice computes. This is what Bob computes. And then we will denote this raising of power by this phi A, which, as you can observe, is a homomorphism from the group to itself. And this is kept secret. So this is a secret homomorphism, really. And obtaining Bob's public value, she will use her secret homomorphism to map to the shared secret. Bob will do something similar. So originally we have phi A composed with phi B acting on G is the same as phi B composed with phi A acting on G again. So this, as I said, is not quantum safe. We'd like to have something else. We kind of want to keep the same structure, but have something else. So instead of using abelian groups, we hope to use something else. And this something is elliptic curves. Or you can even abstract this to general abelian varieties. So we want a map, a secret map that only A knows, Alice knows, that maps from E to EA. And E to EB using a map that only Bob knows. And we kind of want something similar again. We want to have the maps to commute. But isogenies in general, because if you look at this, this is E to EA, right? Because we're no longer dealing, these are groups on its own. So phi A has domain E. And so you're not quite able to put phi A over here because the domain is different now. So this is not well defined for arbitrary isogenies. And how do we solve this problem? Well, there's two strategies to do this. And both strategies would give different crypto systems. So the first one is called SIDH. What it does is that it maps the kernel of phi B through phi A. So I'll explain that in detail later, but that's just the general idea. And then for C side, we have commutative group action on elliptic curves. So this depends on the complex multiplication theory on elliptic curves, and it's really beautiful mathematics. So I'll cover these two things in very briefly. I believe Jana covered this in a lot more detail yesterday in the European summer school. So if you like the stuff that I'm presenting now, do check that on YouTube later on. I'm not sure whether it's on YouTube yet, but it will be when you see in the fullness of time. So I'll just quickly cover what isogenies are because I've been talking about isogenies before. So an isogeny is just a morphism. So a morphism is just some rational polynomials of points. You can think of them like that. So it's an isogeny if it's surjective onto E prime and has finite kernel. And then an isogeny from E to itself is known as an endomorphism. We'll see why that's important later. So there are a few fun facts that you need to know about isogenies. So first of all, on top of being a morphism, which means they preserve a lot of geometric properties, they are also group homomorphisms. So the group structure on E is preserved, kind of, when you move to E prime as well. So addition of group elements on E is preserved in the addition of the mapped points. And secondly, if phi is a separable isogeny, then we have that degree of phi is equal to the kernel of phi. So the kernel plays a very important role in defining the isogeny. And this is encapsulated in this theorem where we have that there's a one-to-one correspondence between finite subgroups of the elliptic curve and separable isogenies. So if you pick a subgroup, you will get a separable isogeny. And from a separable isogeny, you can obtain the kernel and hence a finite subgroup because it's a finite kernel, right? So I've explained how you can go from isogeny to a finite subgroup using, the kernel. So how do you go the other way? If I'm given a finite subgroup, how do I get an isogeny? Well, you can construct an isogeny using Velu's algorithm. And Velu really gives you the explicit rational functions that you need go from one curve to another. So it gives you the codomain, it gives you the how to map the points and all the other stuff. Very fun stuff. And since I'm talking about isogenies, I thought I might as well talk about the isogeny graphs as well. So an L isogeny graph is basically made of two things. The vertices are isomorphism classes of elliptic curves. So these, you can just think of them as just J invariants. And then the edges are L isogenies, where L is the degree of the isogeny. Okay, so yeah, this is what you need to know for now. We might go into that in more detail later. So the most important thing to take away from this slide really is this theorem, that for each finite subgroup, you have a separable isogeny. Okay, so I'll talk very briefly about supersingularity as well. So we have a theorem that for any elliptic curve over Fp, if P does not divide n for some number n, then we have that En, this is the torsion point. So En just represents all the points on E over whatever field you have, such that the order of those points is equal to n. So if you multiply the point, if you add the point to itself n times, it'll give it identity. And this is a structure theorem of those torsion points. It just says there is two copies of the cyclic group. Now, the natural question would then be, okay, what if P is equal to n? What if I want to look at the P torsion, over a field of characteristic P? Well, in this case, what you see is that the P torsion will decompose. Will decompose by losing one bit. So if that happens, it becomes ordinary. If it loses everything and then just leaves the trivial group, then we call it supersingular. So it doesn't just disappear, actually. So if you look at it in the more, so as groups, yeah, they disappear. But as schemes, they don't actually disappear. They just go somewhere a little bit more. All those points just collapse into something a little bit more complicated. But you don't have to know that for now. But this is essentially what it looks like. So this is where things start to get interesting when you look at n equal to p. And more fun facts for supersingularity is the endomorphism ring. So for ordinary elliptic curves, the endomorphism ring is an order of an imaginary quadratic field. So you have many, many different orders. You have one maximal order in the imaginary quadratic field, but ordinary doesn't mean that you have to be the maximal order. You can be any suborder in that. Whereas for supersingular, you have to be a maximal order, but no longer of the imaginary quadratic field. Of something slightly larger is called the quaternion algebra, which is ramified over P and infinity. So the special thing about this case is that the quaternion algebra has many, many maximal orders which are non-isomorphic. And so even though we're restricting to maximal orders here, it's not a very tight restriction. It doesn't just bound the endomorphism rings to just a small set. It's actually a very large one. And one more interesting thing to note is that for supersingularity, curves which are supersingular, we have that the number of points will always be congruent to 1 mod p. Okay, so with this, we have enough to start talking about SIDH. So this is the setup. First of all, we choose P equals to this funny number. So this has to be prime as well. And we're going to set to the n roughly equal to 3 to the m. So this f over here is just to give you more choices to allow p to be prime. So I say again, p must be prime, and it has to take this form with this condition. So then you choose a supersingular curve, just any one, and how you do that is an open problem for now sometimes. And recall, this means that because of the previous fun fact that we have, you can actually even show using some techniques that this has order p plus 1 the whole thing squared. And due to the choice of our prime, we can show that the 2n torsion and the 3m torsion will be defined over fp squared. So that's great. Now, the key thing to note now is that Alice will work over the 2n torsion, Bob will work over the 3m torsion. So let's see how this works. So again, we have the same figure, right? Now we're just going to focus on Alice's computations, which is the top arrow. So there's phi A over here. So Alice will pick a secret, A1, A2. Using A1, A2, she can determine this finite subgroup, right? Just by looking at this as a generator for the finite subgroup. And since this has torsion 2n, this whole thing has torsion 2n as well. So we'll make sure that these two are not simultaneously even. Then this will have torsion 2n, or rather order 2n. And so this determines a subgroup. And then she will compute phi A using value. And since value will give us this thing over here, that is our public key, right? But actually, SIDH requires a little bit more things. So it requires a little bit more information. So what it does is that it needs to compute, Alice needs to compute PB under the map of her secret isogeny. So she will take Bob's points, this PBQB, and she'll map it under her secret isogeny and send it to Bob. So Bob will do something similar. You know, the A's will change to B's, and he will send it to Alice, who will receive this EGB, this phi B of PA, phi B of QA. And what Alice would do now to compute the shared secret is that she will compute this quantity over here. So this is a subgroup. This is now over here, living over here, because you see, these are points over here. So she will take her secret scalars, she'll multiply it this way, and then you can follow it algebraically to see, and also using that phi B as a group homomorphism, that this is actually phi B of GA. So phi B has kernel GB. And now we are quotienting by GA. So long as GA and GB have trivial intersection, then what we have is that they share the same destination, right? Because right now you're quotienting by GA, Bob would then quotient by GB over here. And now on Alice's side, so for the bottom side, you quotient by GB, and then now you're quotienting by GA. So you use the isomorphism invariant, the J invariant of the destination curve as your secret key. And this is SIDH. So basically you just make sure that the kernels have trivial intersection so that they can commute. So they can write it in this form. Okay, now let's look at C side. How does it do it differently?
Yeah, can I ask a question?
Yes, please.
Is there anything specific about these taking a power of 2 and 3, or is it just for maybe efficiency?
Yeah, that's a very good question. So you can choose any prime you want actually, but taking 2 and 3 is for efficiency, as you said, because value, once you compute, so isogeny computations are basically as expensive as the degree. So it grows with the degree. So if you compute, a degree 2 isogeny, it's a lot cheaper than computing a degree 5 isogeny. And this is why we're doing it this way. So when you do all your phi A, for example, this is 2n to n. This is a 2 to n isogeny. What you want to do is to break it down into 2 isogeny, 2 isogeny, 2 isogenies. So you can see this as really a bunch of 2 isogenies. This is where the efficiency comes from. Yeah,
okay.
I hope I answered your question.
Okay, yeah, thank you.
Yeah. So, by the way, I cannot see the questions. So if you do see any questions, please let me know. So for Seaside, on the other hand, it looks slightly different, right? So I'll just go through the general overview first before I go into the details. I just want to see the big picture first. So what you do, what Alice does is that she'll pick a secret A. I'm not going to tell you what A is first, but you just bear this in mind. This is going to be related to the isogeny in some way. She will compute the isogeny, and then she will send A star E to Bob. Bob will do something similar, and she will compute this B star E. Alice will receive it, and then use her A to compute A B star E by using A to act on B. So now we have a few information, some information now, right? We know that AB has to be equal to BA when acting on E. So that's the first piece of information that we have. Okay, so how do we do this? How do we realize this protocol? Well, before that, I'll show you some pictures. So all these are going to be super singular elliptic curves. They're going to have different isomorphism classes. So this is going to be an example of an isogeny graph. So credit to Chloe and Lawrence for sharing these pictures with me. Chloe and Lawrence for sharing these pictures with me. So what you have over here in blue are your 3 isogenies. So you have a 3 isogeny going from this way and this way, there and back. And then the next picture, we have 5 isogenies, and then 7 isogenies. So altogether, this looks like this. And now the question is, well, how do I make use of this information? What you can see, actually, if you look very, very closely, is that this is a cycle. And if you follow the blue, the green and the red, you will also get a cycle. And what you actually have is that isogenies give you a free transitive action on the isomorphism classes. So using enough 3 steps, 3 isogenies or 5 isogenies or 7 isogenies, you can always get from one point to another by sticking on the same color. So the idea is to work with supersingular curves over FP, and then your endomorphism ring is going to look like this with some conditions, on P. Then what you will do is that you're going to consider the ideals of your endomorphism ring, which are going to be this Li, pi minus 1, where Li is going to be some prime. So these are going to be prime ideals. And each ideal over here corresponds to a step in the previous graph. So in the previous graph, I have Li equals to 3, 5, and 7. Now, from here, how do I compute the isogeny? Well, I'm going to compute the isogeny using value. But your question would be, well, where is the finite subgroup? Well, the finite subgroup comes from here. So the kernel of this Li, frac Li, comes from the intersection of Li as a prime number, with the basically points which are defined over Fp. Because if you look at this is the Frobenius. And so what this means is that Frobenius acts as identity. And Frobenius acts as identity only on points which are defined over Fp. And this is where this comes from. And then this Li is basically just the kernel, basically the order of the points. So this really, so the kernel of this fact Li really is points which have order Li, which are defined over Fp. So this is how you use your values formula. So I've explained to you how to compute the path. So now I'm going to show you how to compute this A, which is this your secret. So you want to be able to have many, many different LIs, and then you compute them with different powers. So this EI is your exponent. And notice that because we are in the Dedekind domain, this this A will be able to decompose into many different prime ideals with different powers. And the powers will live in this set. And so we can encode this as just a vector really. A vector with lives and minus b to b, n of them. And one more little point to note is that, so what we saw before, we can either go clockwise or anti-clockwise, and this is determined by the sign of your exponent. But this is just a little implementation issue. So now we've understood how to compute your A. B is going to be done the same way. And since A and B are ideals of your class group, of your endomorphism ring, in particular, imaginary quadratic field, what we can do is that we can look at this in terms of class groups, right? So we can look at the representative of A in the class group and also B in the class group. And we know that class group of an imaginary quadratic field is commutative. So A and B will commute. And we have seen how A and B correspond to an action on the isogeny graph. And so therefore, we have the C side, when you need A and B to commute. And this is it. So these are just some more implementation details. We want to choose primes, which are of this form. So you see that 3, 5, 7, they should all be in this, these will all be primes. And you want to keep this small because, as I mentioned before, answering the question just now, that primes have to be small so that the isogeny computation will be cheap. And then we'll choose supersingular elliptic curves using this form. So this is known as the Montgomery form. This makes implementation easier. And you will notice that due to our choice of prime, all this E, so you have many, many different points of order L, which are going to be cyclic, and they're all going to live and be defined over FP. So these are just some things that will make C-side faster. Okay, so now that I've covered the crypto systems, let's look at some of the attacks. So for C-side and SIDH, we have the simple mid in the middle attack. So what this means is that we are given an isogeny from E to E prime, and we know in SIDH that the prime is the order of the isogeny is 2 to the n. Okay, let's not look at attacking Bob because it's going to be done very similarly. So let's suppose the n is even for simplicity. Then what you do for this attack is that you list all elliptic curves which are 2 to the n over 2 isogynous to E. So you have E prime. You're going to list all these things. So all these are going to be your neighbors, which are 2 to the n over 2, degree isogynous away. And you're going to do the same for E prime. And you're hoping that when you populate these two lists, there's an intersection in the list. And once you find an intersection, all you have to do is to use that point to go back to E and to E prime, and you have found a path in between E and E prime. So this is the basic attack. C-side does something similarly. So you partition this L into 2 sets, and then you list all the different curves. So you do something very similar to C-side, to SIDH. You list all the curves which are going to be L to the alpha I, isogynous to E, and then E prime. You find the intersection between the things in the list, and Bob's your uncle. Okay, so let's look at something a little bit more complicated. So this is where a lot of nice mathematics are going to come from. And the first thing we're going to do is that how breaking Seaside can be reduced to finding the endomorphism ring. So this is motivated by this very deep result by During, which says that if you have a supersingular elliptic curve, then, as I told you before, the endomorphism ring is a maximal order in the quaternion algebra. Now, conversely, if you have a maximal order, then there exists one or two supersingular curves with endomorphism ring O. And in fact, you actually have this bijection, or not really a bijection now, it's a 1 to 2 map. And what's more, you have even something even stronger. You have an equivalence of categories as well. So when I say equivalence of categories, what I mean is that your objects will be isomorphism classes, your morphisms will be isogenies. And on the other side, we have maximal orders as objects, and your morphisms will be something known as connecting ideals. So that will be ideals on maximal orders. So this is kind of like a dictionary. So given a supersingular elliptic curve, you get a maximal order by looking at the endomorphism ring. And then from an isogeny, you can obtain an ideal by looking at this structure. You can notice that E prime, so what happens here is that phi will go from E to E prime, and then you go from E prime to E. So this really lives in the endomorphism ring of E. Okay, and now going the other way, given the maximal order, we can obtain an elliptic curve such that, by constructing the curve from the endomorphism ring. And then given a left ideal, we can obtain an isogeny by looking at the isogeny generated with kernel given by this thing, where this is going to be the intersection of all the kernels of elements in the ideal. Okay, I'll just pause here for a while to take a drink while you digest this a little bit. The upshot that you should take away from this is that there is an equivalence of categories. And so you would think, if I'm able to transfer my problem from supersingular curves over isogenies onto this category, maybe there are some algorithms to solve this problem and bring it back. So that is the hope. And there is indeed such an algorithm. So the first thing is that, well, there's a lemma that shows you, given two endomorphism ring, how you can compute an arbitrary ideal. So you find a general ideal connecting the two maximal orders. So that, it sounds like in the isogenous world is that you have two elliptic curves, you're able to join it with some random isogeny of arbitrary norm. But this is arbitrary norm is not good enough because we kind of want 2 to the n, right? Because that is what we have in SIDH. So this lemma then tells you how to find an ideal of the correct norm by finding an element in the ideal. So now all we need to do is to find an element in the ideal with the correct norm that will give us the ideal of the correct norm. Okay? And so the way to do this is really just to express the ideal as a rank 4 Z module. You do some lattice reduction methods. And because 2 to the n is quite a small element in the ideal, most of the time you're going to find that very element, the very element that you need to use to recover the isogeny or the ideal. So this is really a method where you transfer one problem to another category, solve the problem, and then try to bring it back. But the problem is that the transport between these two categories is very, very difficult because you need to compute the endomorphism ring. And for more information on like how difficult it is to compute the endomorphism ring, you can refer to Cole's thesis, or I think Jana's talk yesterday even covered that. So let's move on to a slightly different attack. So that was very heavy mathematically. Let's look at something a little bit lighter. So this is more crypto. So recall that we have E, and then we have PA, QA, and this torsion subgroup. And this is the secret kernel that Alice uses, right? So we want to try to recover phi A. So the first observation that we make is that, well, if Alice chooses A1, A2 as the private key, such that both are not simultaneously even, then an attacker may assume that the private key is of one of the following forms over here. And this is by just multiplying things by the inverse, the modular inverse of A2 or A1. So let's just make this assumption. Alice uses a static key. And so this is what we have, right? And so our task as an attacker is to find alpha. So we will play the dishonest user. Let's say that Alice is just sitting over there using a static key. I want to find her static key. So what I do is that I pretend to be a Bob that wants to communicate with her. So I'm going to keep sending her different EB PAs and phi B QAs. So I'm going to try to guess all the different EAB or all the different EABs, and I'll try to use this to communicate with Alice. If the communication is successful, then my guess is correct, right? But as we have seen, trying to guess this is not easy. So we need to do this a little bit in a clever fashion. So what we do is that instead of sending this phi BPA, phi BQA, we will send R and S, where R and S are slightly different. So this is what Alice is going to compute, right? She's not going to know what phi BPA and phi BQA are. Okay, so I'm going to send her some R and S. And in particular, I'm going to send her R, S plus this value. So this is going to be a two torsion point, right? Because R is going to be this thing, S is going to be this thing. These are the two torsion points, 2 to the n torsion points. And so this 2 to the n minus 1 S is a two torsion point. I will send this to Alice, and she will plug it in here and here, and this will become, well, you'll see what this becomes. So this will cause Alice to compute either this or this, depending on the parity of alpha, right? Because she will plug in R over here, and then R plus 2 to the n minus 1 S over here. And so if alpha is even, you kill off the two torsion part, and you're left with this. If it's odd, the two torsion part remains, and you're left with this. And you can show that these two are different subgroups, and so they will give you different resulting isogenies. And since this is the original, right, this is phi B PA, phi B QA, this is going to be EAB. And so if I send Alice, try to communicate Alice using EAB, and the communication passes, this means that I know that alpha is even. If I don't manage to communicate with her, then alpha is odd. So I've recovered one bit using this sequence of steps. So repeating this, I can also learn the second bit, the third bit, and eventually all of the bits. So the upshot for this is that you cannot reuse static keys. This is going to be very bad because of this attack. And finally, the last result, because I'm running out of time now, is this beautiful character theory result on C side by Jana, Kestwick, and Vercautren. So the problem is to distinguish two tuples. So I'm writing this in the traditional abelian group, as you saw in the first slide. Yeah. So this is a slightly different problem. This is called decisional Diffie-Hellman problem, or DDH. So you're given this tuple and this tuple, where A, B, and R are unknown and random. Okay. And the problem, the task for you is to distinguish between the two of them. So let's see how we can solve this if we have something known as a character. You have a character that is able to take in this any element in the group, and this is our group now, and it spits out 1 or -1. Then I argue that we can solve a large number of instances of this problem. And this is how you do it. Yeah. So we take the Legendre symbol. This is our character. And suppose that G evaluated with P equals to -1. Then what you're going to do now is you're going to evaluate G to the A at P, G to the B at P, G to the AB at P. Yeah. So, and you're going to evaluate all this. And because you can work out the parities of AB and AB, because this is -1 and this is multiplicative, you can test the consistency of the DDH distribution. And so you can tell whether something is a correct DDH distribution or not. So this is how you can use a character to solve the DDH problem for a large number of instances. So we'll do something similar now. The task now is to distinguishing two tuples, the first one over here and the second one over here, where A, B, and R are random. So how do we construct a character? What we want is to construct this character, as we said, where you plug in your ideal and it spits out, ±1. So this M over here, we're not going to use the characteristic of the field. We're going to use this M, which is prime divisor of the discriminant of the quadratic field. So I'm going to skip a lot of details because, yeah, I think you're going to see this presented in crypto, and yeah, I look forward to that. So I'm just going to give you a skeleton of the attack. So why is prime going to have to be? Why does M have to be a prime? I'm going to leave that for the crypto talk. And we're going to let phi A be this isogeny. Okay, so this is our aim. We want to evaluate the ideal at chi. But the problem, so the first observation is it suffices to compute the degree of phi A, right? Because this is norm of the ideal, which is using the equivalence of categories, is the degree of phi A. So we don't need to know what the degree is. We just need to know the degree mod M. But the problem is that we do not have ideals, right? What we get are E, AE, BE, ABE. And so these are actually elliptic curves. We never actually deal with ideals. And this is where the security of C set comes from, that we don't actually see the groups in action. We see how they act on the set. We only see set elements. So the group is hiding behind the set. Now, so we have E and EA. How do we use that? So what you're going to do is you're going to use the points. The observation is that you have P and Q, M torsion elements. You can compute, this relation holds. If you can compute phi P and phi Q, then this would hold. And so you can obtain this, you can see phi, the degree of phi coming over here. So this is what you want. But the problem is that you're not able to compute phi of P for arbitrary P because you don't know the isogeny. So you cannot compute this for arbitrary P. So what you do is that, well, okay, let's take a P in E and just take a random P prime in E prime. Then I know that P prime is going to be some scalar multiple of P under the map. So this is under assumption that this group that they're in is cyclic. And you can see why it's cyclic in the paper. So it's important to know that this is cyclic, and so therefore we do have this relationship. So if this is true, then we can evaluate P prime under the Tate pairing, and we have this relationship. So we have the degree of phi. You can solve this using, the usual discrete log problems, the discrete log oracle, because M is usually quite small, or some doable number. So once you can do this, you can recover this number, M, you can plug it in here. The only problem right now is this K square, but it doesn't matter, right? Because this is going to be a Legendre symbol. K square is just going to be evaluated to 1. And so therefore you do have your character now. And so therefore you're able to then break DDH for C side. And this is just, I don't know, a very, very beautiful result. So what I've covered today is 2 schemes, both of them post-quantum secure. I haven't talked about, post-quantum security yet. For more results on that, you're going to have to, speak to any one of the friendly isogeny people during the seminar. So we have SIDH and C-side, where both of them use different methods to get around the commutativity issue. Okay, and I also presented mathematical attacks on the schemes. We looked at adaptive attack, computation of endomorphism rings, C-side, and also mid in the middle, So the upshot for this attacks are that you cannot use static keys. C-side, SIDH is still safe because it's still very difficult to compute endomorphism rings. And C-side DDH, it's still, C-side is still safe because we need P congruent to 1 mod 4. But C-side uses P congruent with 3 mod 4. So, and you don't really use decisional SIDH most of the time anyway. So yeah, this is the end of my talk. Email me your questions or talk to me on Zoom during the social session later on, or whenever you're free. And I'm going to flash this slide. This is the references. If you're on YouTube, just pause this for more information. Yeah, thank you.